Okay, so the first circuit that I will build is the one that you're looking at right now, but without the capacitors. I'm going to use the capacitors later as debouncers, as hardware debouncing, just to see the difference. But let's start with the bare bones version of the circuit. I'm only going to include the pull-up resistor so that the button works properly. So let's start by plugging in the Rotary encoder. Got to remember that the first pin on the left is ground, then I've got power, then is the button pin, DT and CLK. I'm going to plug in the pull-up resistor. Then let's go for 5 volts power. Oops, made a mistake. So the pull-up resistor should go on the button like that. Okay, so red wire for power. I use black for ground. Actually, I'm just going to use the power rails here for those things. So I'm going to plug that here and that here. And let's take blue for ground. And another red for 5 volts. Okay. And because I wouldn't want my jumper wires to escape, I'm going to stick them together. This is very important because I'm going to do a bit of measurements later and using the oscilloscope, and I wouldn't want any slight movements of the jumper wires to skew my results. So I'm just going to make sure that these contacts are solid. And this Arduino is very old as well, so the contacts inside have already worn off. Alright, so that's it now for the button. I'm going to connect it to digital pin 8. And I'll use an orange wire to connect DT. DT will go to digital pin 3. And let's make a green wire for CLK to digital pin number 2. Now we'll see later that the sketch that I'm going to use uses the interrupt request feature, which is available on digital pin number 2. And that's specifically why I connect the digital pin number 2 to CLK. Alright, and I'm also going to make sure that these three jumper wires are not going anywhere and they're not moving as much as possible. Okay, done. Let's plug power, upload the sketch. Make sure it at least works partially. It's not going to work very well, but to see how much it works. And then I'll go through the sketch and explain what it does. All right, there you go. Done. Let's bring up the monitor. I'm going to hold down the rotary encoder with my finger to make sure that its connections are solid and turn it to see what's going on. All right, so you can see as I'm turning it, on one side, one direction, okay, numbers are increasing, counts are increasing. Other direction, kind of, nah, it's a very noisy signal, so I can't really see what's going on here. Right, so there's a lot of noise in this channel. And I'm going to bring in my oscilloscope leads, and I'm going to plug the yellow one to the one that I will use as trigger. So that's CLK. I'm going to plug CLK here. I also need to ground the oscilloscope lead. So I'm going to use another extension, another jumper wire, and plug it into the ground rail. And for the second channel of the oscilloscope, I'll use the orange lead. And again, I'll ground that here. Okay, now on the oscilloscope side, I'm going to use I'm going to do a single capture, and as I turn the knob, you can actually see that there's a quite clear signal. Interesting. So the signal that I just produced is quite clear. So the yellow is the CLK and the blue is DT. Let's try this one more time. So as I turn the knob now clockwise. Okay, so as I turn the knob clockwise, you can see that the DT, just double check. So blue goes to orange. So orange is DT. Orange goes to blue, so the blue signal here is DT and is the one that is grounded first. So that goes first, then you've got clock, which goes down later. So you've got a signal here which is 0, 1. And also you can see there's a bit of noise here and a bit of noise here. If I zoom in the blue channel and increase the time, here you can probably see it. There's a bit of noise here that could confuse the Arduino in its readings. I'll do a couple more measurements to see what it looked like, just to average out. So yeah, you can see a bit of the bouncing noise here and here that went all the way down. Do one more. Okay, so this is clockwise. You can see there's one, right? And one more clockwise. Right. Go. Blue first, yellow second. We didn't pick the blue change in state, so the still doing clockwise, but the yellow this time went first. So there's a lot of issues here. So when you've got the blue first and then the yellow drop, the Arduino detects a clockwise movement. But when you've got the opposite, let's see if I can generate one more. So blue first, nope. If we have yellow first, I did it earlier, but let's see if I can do it again. Nope. Oh, you have something like this, or is it a really bad signal? Something like this, or this, yeah. Anyway, it's inconclusive. The signal is not very clear. So that's why the Arduino is getting a bit confused about which way the knob is really turning. Right, so if I press it, I go to reset. Before we see how we can improve the situation, let's have a look at the sketch. This is the unbounced version of the sketch. So I set up the pins first. So pin CLK goes to 2, DT goes to 3, and the button goes to 8. This is how I keep track of the virtual position of the knob, and I'm declaring this long variable as static because I'll be referencing it from inside the interrupt service request routine. I'm going to come back to this interrupt service request in a minute. in the setup function, I set my pins to be inputs, and I attach interrupt. Now in the ATmega 328, interrupt 0 is a hardware interrupt that is implemented in digital pin number 2. So here I'm saying that I'm going to attach an interrupt request, which is going to trigger when the waveform goes from low to high. And when that happens, I want to call routine ISR 0. You can change the name if you don't like it, but I call it ISR because it reminds me that this is an interrupt service request routine, and it's the zero interrupt service request, and it's a zero interrupt service request routine, which is attached to digital pin number 2. I start the serial ports. I can get some output shown to the user, and then in the loop, you've got the counter set up. It's an integer, and it just goes around and forever. So while this is true, it just tells me what the last count is. Now, when I turn the knob, I generate an interrupt request, and my ISR routine fires. So the Arduino is going to call this routine. The first thing I'm doing here is to detach the interrupt so that I cannot interrupt the interrupt. So I'm saying detach interrupt at pin 2, which is interrupt 0. So I'm taking a reading from digital pin number 3, where the DT pin is connected to. And if it's low, then I'm detecting a virtual position, a clockwise move, and I want to increase the virtual position variable by 1. Otherwise, decrease it by 1. So this way I can increment or decrement this counter. Back in the loop, we are forever in the while loop, and we'll check to see the status of the button, and if the button is pressed, then reset the value of virtual position variable, make it back to 0. Now, because I don't want to be constantly outputting new virtual positions unless the virtual position has changed, here I'm just checking first to make sure that we do have a change in the virtual position that is not the same as last count. And if it isn't the same as last count, then update last count in the local variable in the loop with the value in virtual position, and then print it out. Okay, so we know now that without hardware debouncing, we're not really getting really good results. So let's go and add some hardware debouncing in the next demo.